Hi, I'm Katie Steckles.
And I'm Peter Rowlett. And hi, Katie, what's today's mathematical object?
Well, today's object is a hairy ball. And that is sort of literal, but I guess not because it's a maths thing. But it is possibly one of the funniest named theorems in the whole of mathematics, is the hairy ball theorem, which is on the subject of a ball covered in hair.
Yeah.
I guess. So it's from the field of algebraic topology, which is to do with looking at shapes and looking at different ways to study them and analyse what's going on with them. It's a theorem which is sometimes also called the hedgehog theorem in some countries, and essentially it concerns a sphere. So I guess if you want to imagine it, it could be a three-dimensional sphere which has at each point of it attached a hair, which is sort of a vector, but you can think of it as a hair.
Or a hedgehog spike.
Or a spine on a hedgehog. Yeah. And it can point in any direction, but it is attached to the sphere at that particular point. So that's the sort of notional object that we're thinking about.
Yes, I liked the bit where you said, if you want to visualise it, you can imagine it being a 3D sphere. Like, if you're that way inclined.
Yeah, well, this is the thing, because in topology and in maths in general, the number of dimensions can be anything. So yeah. If you ask me about a two-dimensional sphere, I would be thinking about a circle. If you ask me about a one-dimensional sphere, I guess that's a single point. No, it's not. It's 2 points, because a sphere is defined as the set of points that are the same distance away from the centre in that many dimensions. And a one-dimensional space is just a line. So you'd have a point in the centre, you'd have 2 points equally spaced either side of it. That's what a one-dimensional sphere looks like.
Okay. And the 2 points either side of the sphere, not the point in the centre.
Yeah. The point in the centre is just defining the sphere, I guess.
Yeah.
But of course, because topologists are awkward, they would call such an object a zero sphere. They would call a circle a one sphere, and they would call a sphere in 3 dimensions a two sphere, because it is a two-dimensional space, because you can define any point on the surface using 2 coordinates.
Yeah, so this is because it's a 2D object embedded in a 3D space.
Yeah. Yes, but I, for the sake of simplicity, will refer to a 3-dimensional sphere as the object that you can kick if you are a footballer. Okay, so for the avoidance of ambiguity, that's what I mean by a 3-dimensional sphere. I mean, obviously, a 2-sphere. So I've got this 3-dimensional sphere. It's got a point. It's got a hair attached to every point, which I guess in the official mathematical world is a vector field. So it's a set of vectors defined at each point, and they can point
isn't
in
like you've got some lines of longitude and latitude, and wherever they cross, there's a thing, and there's only so many of them. This is infinitely many hairs.
I guess it's attached to every point on the sphere, which is like a continuous surface. But in visualizing it, you're probably imagining finitely many hairs, but it's notionally a vector field with a vector at each point. And we are trying to, I guess, comb the sphere. So if this was a person's head, which weirdly has hair around the front and underneath as well, you were trying to comb the hair. And you want to do that in such a way that it is continuous, which is a maths word, I guess, which means that it sort of behaves in a sensible way. So each hair is sort of roughly pointing in the same direction as the one next to it and isn't too far away, and you don't have any big jumps in what direction things are pointing in. And because we're combing it, we're going to end up with a vector field made up of tangent vectors. So each hair lies flat against the sphere and points in a direction.
Right.
So, in the mathematical sense, we're thinking about tangent vectors, not vectors that point upwards or in other directions. We're combing it flat.
So in sort of the hedgehog had laid down its spines and they're all in the same direction in some sense.
It's a very chilled out hedgehog. Yeah, its spines are not pointing upwards in the air anymore. They are combed flat. But yeah, the question, what direction are they all pointing in? Because they're pointing, like, they don't all have to be pointing in the same direction, but ones near to each other kind of have to point in a similar direction. Okay. So you could have hair on one side pointing one way and hair on the other side pointing the other way, as long as there's like a smooth gradient between the two.
Right.
I guess. So the whole thing is continuous. And the hairy ball theorem, which, as I mentioned, is the funniest named theorem in maths, basically says that there isn't a way to do this for a 3-dimensional sphere. There isn't a way to do this without somewhere the hair sticking up, I guess. There isn't a way to do this consistently. And I have said that we're talking about tangent vectors, so the hair should all, in theory, be flat. But I guess what I mean by sticking up is, in the vector field sense, the only way for it to work is if that vector becomes 0 at that point. So it becomes a 0 length vector and vanishes. And I guess the notional analogy for this, since people love those, is at the back of someone's head, there's often a bit where the hair sort of twists round into a little point, and it's called a cowlick. And that is a point where the hair is kind of vanishes, because in practice it means your hair sticks up away from your head a little bit, but it's essentially you can't comb the hair such that you don't have that bit. And
so I'm thinking a bit about a circle, since you brought up a circle.
Yes.
So if I start at let's say the top of a circle,
yeah,
and I brush half of it one way and half of it the other way, then the opposite side I'm going to have two bits that bang into each other. But if I brush it all in one way, I can just keep going around forever.
You can. So the hairy ball theorem doesn't apply to a two-dimensional sphere. In fact, it alternates. So you can only do the combing in an even number of dimensions. Okay. So you can do it in 2D. You can do it in 4D. Right. Which is interesting because that's really hard to picture. And I read about this. It's absolutely brilliant. So if you imagine there was a way to comb it on a 3D sphere, you might imagine parting the hair around along a circle around the middle of the sphere. Okay. Right? So if you're doing it in 4 dimensions, that's what you do, except because you're in 4 dimensions, the thing you part it along is a 3-dimensional sphere.
Of course.
Yeah. And so you can part it quite happily along a 3-dimensional sphere, whatever that means, in 4 dimensions. Or, if you prefer, you can part it along the surface of a torus. Okay. Those are both perfectly good ways to do it in 4 dimensions. In 2 dimensions, as you say, you can do it by just combing it all around in the same direction, and that works. But in 3 dimensions, because of the geometry and the way it all fits together, you just can't do it. So that you have to have at least one point where it vanishes. And it's really nice. You can sort of picture, a hairy ball that you comb all the hairs around the same direction, around the middle, around the equator. Yeah. If you carried that pattern on upwards and downwards, you would end up with discontinuities at the top and bottom. You'd end up with the sort of poles. The reason for it is actually quite nice. So the Euler characteristic of a shape, which is a topological property that a shape has, which determines various things about how things join up on it. If you know anything about Euler characteristic, for a sphere it's 2, and for a torus it's 0, and it's to do with the number of holes in the shape, but It tells you something about what flat things look like on that shape and that sort of thing.
Yeah, I'm terrible at remembering names of things. It's sort of why I'm not a biologist, and because it's named after Euler, I'm like, oh, okay, that could be more or less anything.
Yeah,
it's the number of holes thing. It's the coffee cup donut.
Yeah, so it's 2 minus 2 times the number of holes.
Right.
So for a sphere, it's 2, and the property that relates to the hairy ball theorem is that if you have a surface with Euler characteristic, whatever it is, that has to be the sum of what are called the indexes of the poles. So it's not necessarily important exactly how you calculate the index of something, but if it needs to be equal to 2, you can't do that without having at least one pole, or one cowlick, I guess. So you can do a thing on a sphere where you've got 2 and they both have index 1 and they add up to 2. You can do it where you just have one pole. And there's a really nice gif of this on the Wikipedia page for the hairy ball theorem, but it sort of shows that they kind of you comb it all in the same direction around underneath the sphere, and then on the top you end up with this really cool sort of 2-dimensional discontinuity that looks a bit like a magnetic field for a bar magnet. It sort of comes in from both directions and goes out from both directions, but you have a single point there which has index 2, whatever that means, so that satisfies the property. But because a torus has Euler characteristic 0, you can comb a hairy torus.
Yes, okay. So I'm making a little list of things. You've mentioned magnetic fields and you've mentioned the torus. So torus is a good one to start with, yeah.
Yeah, well,
because the torus is just a load of circles, right?
Yeah, it's circles crossed with circles. So if you imagine combing a hairy torus, it's kind of like the circle. You just comb it all around in the same direction. And that works perfectly fine. I did actually build a model of a sphere and a torus and then cover them in fur fabric in order to be able to hold them up and talk about this at I think it was at a festival once. But it is really cool because you can just see it all kind of happening. It all just quite happily lays flat in the same direction. So it is not just the number of dimensions that determines whether or not this is possible. It's also the properties of the shape and the number of holes in the shape. And I guess if you had a shape with 2 holes, because then your Euler characteristic isn't 0 anymore, you wouldn't be able to do it again.
Yeah.
So that's that.
But if you had enough holes that then you'd be able to sort of, each bit would wrap into another hole and
it gets messier.
Yeah.
But yeah, so it was, for anyone who's keeping track, it was in 1885, and the original hairy ball theorem was proved by Poincaré, famous for doing lots of maths and topology and stuff. The higher dimensional stuff, so Poincaré did 3-dimensional spheres. The higher dimensional stuff was Brouwer in 1912, but it does alternate, so the number of dimensions, if the number of dimensions you're working in is odd, you can't do it, and if it's even, you can.
Okay. If the number of dimensions is odd and you're a 0.
Yeah.
Okay.
There's a few properties that need satisfying, but yeah, it's for a sphere, I guess it alternates, and that within 3-dimensional space, there's some things you can do and some things you can't do. But yeah, it's sort of nice. It's a funny thing to talk about. Because people are amused by the name. In fact, one of the things I found while I was sort of digging out some extra facts about this was that it was a question on the BBC TV quiz show The Chase, which was, they said, in algebraic topology, which one of these is a real theorem? And they had, as they always do on The Chase, they had the correct answer and 2 obviously made up answers. But if you didn't know it was a theorem, the obviously made up answers weren't that obviously made up. It was like the furry plum theorem or the...
Right.
And they got it wrong, because how would you possibly guess? But also the chaser at the time was Marc Lebet, who is actually a mathematician.
Right.
And he said afterwards, I've studied topology and I've never heard of this. So it's obviously not a funny enough name, because you would think that people would definitely have heard about it if you give it a ridiculous name like this. Or the hedgehog theorem is such an adorable name for a theorem. Yeah. It's really nice. I think one of the nicest things about it is that it kind of has an application.
Okay.
Because obviously vector fields are a thing that they use in physics to study, as you say, magnetic fields and things like, fields of motion. And one of them that you can do really nicely is think about wind on the surface of a sphere, because obviously we live on the surface of, topologically, a sphere. The direction in which the wind is blowing is roughly a tangent vector, sort of ish. You can model it that way. So what it means, a direct consequence of the hairy ball theorem, is that at any given time, there must be at least one point on the Earth's surface where there isn't any wind.
Yeah. Which
is quite a nice, interesting thought, and it's completely useless because it doesn't tell you where that is, or yes. What. Or how many there are or anything, but they're, somewhere on the planet right now, someone's just stood outside and gone, it's not windy at all.
Yeah.
Or hasn't noticed or whatever. And then I guess the sort of maths implications are also things like if you have a function that maps a sphere onto a sphere, it's got to have at least one fixed point, or I think it's either has to have a fixed point or has to have a point that's mapped to its antipode.
Okay.
Like a point that maps to its exact opposite, because the function itself has to kind of obey all the same rules. So, it has applications. I'm doing finger quotes around that in generally thinking philosophically about things. But I imagine if you're studying sort of physical systems and things like that, this kind of insight is useful. So
yeah, good. Right, good. So we're on Twitter. I am at Peter Rowlett.
And I am at Steckles, and the podcast itself is at Maths Objects.
We both blog at a website called aperiodical.com, where you can find more episodes of the podcast if you want to hear more of us chatting away about mathematical objects.
And if you have any contributions to make, if you have any suggestions for other objects that we could talk about, you can send us an email at objects@aperiodical.com.
The music is Funky Game Loop by Kevin MacLeod, licensed under Creative Commons.